Hello, here is the low delta T optimization strategy. As an example, I have named the building zone A, B, C, and D.
Are you facing the same issue in your building? Our secondary side delta T mitigation strategy can help.
Picture this, a brand new state-of-the-art building. Looks perfect, right? But what if I told you it was secretly hemorrhaging money and energy because of a flaw that no one can see? Well, today we're going to play detective. We're going on an investigation to find this invisible thief and uncover how one hidden problem can cost a fortune. So, how on earth does that even happen? You'd think a new building would be the poster child for efficiency. But the truth is, the more complex a system gets, the more little nooks and crannies there are for problems to hide. The very first step in this whole investigation wasn't to start tearing things apart, but to hunt down the root cause of this massive energy drain. And here it is. Meet the villain of our story, low delta T. Sounds technical, but it's pretty simple. Cold water gets sent out to cool the building, right? Well, it's supposed to absorb a lot of heat and come back much warmer. When it comes back only a little bit warmer, that's a low delta T. It's a huge red flag that the system isn't working right, and it forces the pumps to work way, way harder, just burning through energy to do the same job. And we're not talking about a small-time issue here. The setting for this investigation is a massive complex with 4 separate zones: A, B, C, and D. Each one has its own chilled water system. That means the problem could be hiding in any one of them, or all of them. So with a place that big, where do you even begin? You start with the data. That's right. Before anyone picks up a single tool or even steps foot in a mechanical room, this whole investigation kicks off with a deep dive into the building's digital footprint. This isn't about guesswork. It's about building a case based on cold, hard evidence. The entire investigation really boils down to this one key comparison. On one side, you have the design intent. That's the blueprint, how the system should be working on paper. And on the other side, you have the operational reality, what the live data says is actually happening right now. The problem, the real culprit, is always hiding in the gap between those two. And to find that gap, you've got to assemble your case file. We're talking everything: the original CAD drawings, the schedules for all the equipment, and the commissioning data that proves the system actually worked correctly at one point. But most important of all are the real-time data logs from the building's own management system. The first clues are always buried right there in the data. Okay, so once the data has pointed you in the right direction, it's time to get your hands dirty. This is where the investigation moves from charts and spreadsheets into the real world of pipes, pumps, and machinery. The physical search starts right at the source, deep in the mechanical heart of each zone, the energy transfer station rooms. Think of these as the central hubs where all the chilled water is managed and sent out. You know, if there's a problem at the very core of the system, it's going to affect everything else down the line. First up for inspection are the big guys, the primary pumps. A total of 12 of these pumps across the 4 zones are put through their paces. Testers are checking to see if they're operating on their pump curve. That's basically their optimal performance line. Any little deviation from that curve is a major red flag for wasted energy. Next on the list are the 8 massive plate heat exchangers. These things are absolutely critical for actually transferring the cooling energy. The team goes over everything: flow rates, pressure, temperatures, to make sure they're pulling their weight. An inefficient heat exchanger can lead straight back to that low delta T problem we keep talking about. So, after the central equipment has been thoroughly checked out, the investigation expands. It moves outward from those core mechanical rooms to the hundreds and hundreds of terminal units on every single floor. This is where the cooling actually gets delivered to people, and it's where a ton of small problems can add up to one giant headache. And the scale of this is just huge. You can't possibly check every single one. So the team takes a large random sample, 100 fan coil units, those are the things in rooms that actually blow the cold air, in the common areas, and another 50 inside the private apartments. They're checking everything from water flow to whether the control valves are actually listening to the thermostat. So as you can see, this isn't just some random walk around. It's a methodical top-to-bottom audit. every single piece of the puzzle gets checked, from those big pumps and heat exchangers down to the individual fan coils, sneaky bypass lines, and even the tiny sensors that are supposed to be feeding accurate data back to the main system. You leave no stone unturned. And here is a really common culprit, something you might never even think about. A lot of the time, the chilled water just finds a shortcut. A valve that's stuck open or a pipe that's not connected right creates a bypass, letting that ice-cold water loop right back to the central plant without ever doing its job. It's one of the classic invisible thieves of energy in these systems. So, after all that digging through data and crawling through mechanical rooms, what happens next? Well, this is where it all comes together. The final phase is all about turning those discoveries into a crystal clear, actionable plan. This is the roadmap to fixing the problem for good. And you might think a project this detailed would take forever, but it's remarkably efficient. The entire investigation, from grabbing the data to weeks of on-site audits and then the final analyses, is all wrapped up in just 8 weeks. That gives the building's management team the answers they need, and fast. And the outcome isn't just a quick summary, it's a whole set of concrete, super detailed reports. These documents spell out every single finding, from how the main pumps are doing all the way down to how individual little actuators are working. And it all leads to the most important document of all, a detailed rectification plan. Now, it's really crucial to get this distinction. Phase 1, which is everything we just talked about, is the diagnosis. It's all about finding the root cause. Phase 2 is the cure. That's the hands-on work of making the fixes, recalibrating the valves, and tuning the entire system based on what was found in Phase 1. You have to find the problem before you can fix it. And this all brings us to one final, really important thought. Our buildings are constantly talking to us. They're generating this huge stream of data every single second of every day. This investigation proves that the clues we need to make them smarter and more efficient are hidden right there in that data. So the only real question is, are you listening?
Thanks for watching the video. Subscribe for more videos.